So we've talked about linear momentum, we've talked about impulse. Now we can talk about a concept called the conservation of linear momentum. Now, conservation of linear momentum occurs in collisions or explosions. Now, collision is just a brief, large magnitude force that can dramatically change an object's momentum. If you think about it, that kind of fits the explanation of an explosion as well, like a firework exploding, where you have a brief, large magnitude force that dramatically changes object's momentum. You have a bomb that goes off, little pieces of the bomb explode outward. In both cases, the linear momentum of the system is conserved. And let's look at what we mean by a collision. So here we have two objects, mass 1 and mass 2. Object mass 1 has some initial velocity, v sub I, v sub 1I. Object 2 is going to the left, it has some velocity, v sub 2I. They collide, exchanging forces. So there's a force on 2 from object 1 during this collision, and there's a force on object 1 from object 2 that's equal and opposite. That dramatically changes the velocity of the objects, their momentum. And now object 1 is moving to the left with some final velocity, which doesn't necessarily have to be the same magnitude as the initial velocity. And object 2 is moving to the right now with some final velocity. So when we look at an individual object, the individual objects here, the momentum absolutely changes, right? You have an object going to the right, so the momentum is to the right. Then you have a collision. Now this object is moving to the left. And remember, momentum, like velocity, is a vector. Direction matters. So here we have the object moving to the right. Here we have the object moving to the left. So M1, object 1, definitely had a change in its momentum. Object 2 also definitely had a change in its momentum. It started off moving to the left, collided, now it's moving to the right. So when we look at the individual objects, momentum is not conserved, right? This has a positive momentum, now it has a negative momentum, defining right to be positive, left to be negative. This had negative momentum, now it has a positive momentum. However, if we look at this system, if we treat the two objects as a system, then all the forces that are exchanged between these two objects are in the system. They're all internal forces. There are no external forces in this system, right? There is no friction, there is no drag force, there is no outside force influencing this collision. So we can ignore external forces during a collision, and it's a pretty good approximation. So we don't have to worry about external forces acting on this system. And when we ignore external forces and we treat the two objects as a system, something interesting happens. So writing this out, we talked about the impulse and how the impulse depended upon the net force acting on the system times the change in time that force is acting. Now, this net force is external to the system. So if we consider the system to be the two blocks or two balls colliding together, there are no external forces acting on that system. If there are no external forces acting on the system, if the net force is 0, well, 0 times any time is 0, so the change in momentum has to be 0. If the change in momentum is 0, that just means momentum can't change. Before and after a collision, the momentum must be the same. So in other words, of writing that is the momentum before the collision, remember it is a vector, must equal the momentum after the collision. In the case of the two balls I drew earlier, the mass of ball 1 times the initial velocity of ball 1 plus the mass of ball 2 times the initial velocity of ball 2, right? This is the momentum of object 1, this is the momentum of object 2, has to be equal to the momentum of ball 1 times the final velocity of ball 1 plus the momentum, the mass, not momentum, the mass of ball 1 times the final velocity of ball 1 plus the mass of ball 2 times the final velocity of ball 2. This is the momentum of ball 1, this is the momentum of ball 2. So the total momentum of the system has to be the same before and after. This is very powerful because we can use it to talk about the results of collisions. And we're going to start in the next video by just talking about the very simplest of collisions, those in one dimension, so those constrained. So if you think of a pool table, when you have a billiard ball striking another ball, sometimes that ball, the billiard ball hits and the ball goes off straight. Other times they can go off at angles. So we have to decide, we're going to constrain our study to first talking about one-dimensional collisions, and then we'll expand into two-dimensional collisions.